A lot of us think in big waves we need big fins. Actually, it's the opposite. Once you understand how fins work, you will see why a smaller fin is the better choice in big waves. First of all, what does a fin actually do? A good way to see that is to watch what happens the moment a fin breaks.
And it was feeling pretty good. And then I think the very next wave I was flying down the line and getting really excited about laying into a layback and then blew out on the bottom turn.
Now one more time in slow motion. Watch how the board slides out the moment the fin breaks. What happened? We have the board and the wave. We are making a bottom turn, so the board is on its rail. Half is in the water, this part, and this part is above the water. One fin is in the wave and the other one is out. We can see it a bit better here. This is the wave, half of the board is in and half of the board is out. So only one fin in the water. If we look under the water, we can see here the water flow on the fin. If we look from the top down through the board, we can see the water hits the fin at an angle. Now let's go back to the view under the water. Again, this is the water flow, and this flow creates a force on the fin, this green arrow. We usually split this force into two parts. One part points in the direction of the water flow, we call this one drag. The other part is perpendicular to the water flow, and this one we call lift. This word lift is often misused when we talk about surfboards. It comes from the world of airplanes. On an airplane wing, the airflow creates an upward force. That's how planes stay in the air. The part of that force, perpendicular to the airflow, is called lift. Over time, lift became the general name for this part of the force. On our fin, it's a side force, and it actually points downwards into the water. So don't get confused, lift is not up. It's simply the part of the force that is perpendicular to the flow. We split this force into two parts, because there's one part we want, this lift, and the other one, drag, we don't want, but we can't avoid. Drag pulls you back and slows you down, so we try to keep it minimal. Lift is the part that keeps the board in the water. You could say it gives us grip. Still, it's just one force with two parts. So if the fin goes, that force goes as well, and then the buoyancy pushes the board out of the water. Let's go back and watch it again. Right about here, the fin breaks. Now there's no force holding the board in the water, so the buoyancy pushes the board out. Now let's take a closer look at these two parts. First, the lift. That's the one we want. So here is the formula. I know most people don't like formulas, but this is the only way to see how we can actually influence this force. This is the water density. It always stays the same, so we don't have to worry about it. This is the speed of the board. Important here to notice, speed is squared. This is the fin area, how big or small the fin is, and this is the lift coefficient. This coefficient is determined by the shape of the fin. Now drag. Drag has almost the same formula. The only thing that changes is the drag coefficient instead of the lift coefficient. The speed is still squared, the fin area is there as well. Now let's take two scenarios. Scenario 1 is a 1 meter wave, scenario 2 is a 6 meter wave. Speed on a 1 meter wave is about 20 kilometers an hour. On a big fast wave it can be around 60 kilometers an hour. So if the speed is 3 times bigger, the force is 9 times bigger, because remember, the speed is squared. This means on a 1 meter wave, the lift is about 7 kilos. Picture it as a weight of 7 kilos hanging on the fin. On a 6 meter wave, it's 63 kilograms. That's the weight of a person hanging on the fin, pushing it into the wave. That's a lot. For drag on a 1 meter wave, it's 0.6 kilograms. On a 6 meter wave, it's 5.4 kilograms, pushing us back and slowing us down. And that's just on one fin. Now, why are these forces too big? First, with these forces, you can't push back anymore. The board decides the line, not you. The force is simply too much to correct with your legs. Second, a small mistake has a big impact. 1 degree off in these big waves, from a bit of chop for instance, adds several kilos instantly. So the board suddenly grabs or chatters. And then third, drag is a constant brake. That's the part we don't want anyway. You need the speed to make sections or outrun the lip, especially on big waves. So in general, the extra force we receive from the fins in big waves is much more than what we need. Now what can we do to reduce the forces? There are two ways. We can reduce the fin area and we can reduce the coefficients. To reduce the fin area, we can, for example, go from a large to a medium or even to a small fin. Going from a large to a small fin reduces the forces by around 10%, so that's an easy first step. The other thing we can reduce is the lift and drag coefficient, and we can reduce that by choosing a flat foil instead of an inside foil. That lowers the forces by another 15%. To give an example, in FCS we can go from a performer large to an accelerator medium. By this we change both size and foil. The performer fin has an inside foil, the accelerator fin has a flat foil. By doing this, we reduce the lift by about 20% and the drag by about 12%. And that's enough to bring the forces back into a range that we can control. To conclude, if you surf big waves and you have the option to change your fins, consider going down a size and using a flatter foil. In this video, we looked at the impact of only one fin. What happens with thruster or quads is a lot more complex, of course, and that's material for another video. And if all of this makes you wonder what the right surfboard is for you, we've built this kind of knowledge into a tool called Magic Board Finder. So if you struggle to choose a board, take a look at magicboardfinder.com. It's totally free. The link is also in the description below. Thanks for watching and see you next time.